All right, everybody. This is Shinga. Happy New Year to everyone who I haven't said Happy New Year to, which I suppose would be most of my listeners. You are listening to SG2 on Space, the only weekly space show here in Houston. Now, with this new year, I got some major announcements for you guys. So first of all, still with Action One Media Group, as you can see. None of the links have changed, so still follow me, listen on facebook.com/The Shen Show, support me, patreon.com/SG2 on Space. Now, what has changed is the time. Previously, it was on Thursday nights live. Now we've shifted the time to Saturdays. Today is a little different, and we're doing it from 1:55 to about 2:30. So we are cutting it down to, maybe not, shouldn't use the word cutting it down. We are going to be a half-hour segment. So in the future, it's going to be on Saturday at 1 p.m. Houston time once again. So it'll be from 1 to 1:30. You guys can tune in there if you want to hear it live. And, if you can't make it, then, of course, you can go on YouTube and listen to all the shows. All the previous shows are going to be there, hopefully forever. And that's about it. So I will repeat this announcement at the end as well. So today, given that I was thinking it's a new year, 2020, I was thinking about the concept that of time, how we define it. So it seems like, we got this. We have this concept that's fairly abstract. We think we know what it is. I mean, you count it by seconds, minutes, hours. And you say, okay, so like for instance, I just said it, right? I was like, yeah, we changed our time to Saturday at 1 p.m. in the future. But really, how are we really defining that? So physicists, we always assume that we are passing in one direction, the arrow of time, right? And what that means is that you're not going to go into the past. We're always going to the future. Although, me being a little strange, I think there may be some stuff out there where, like in the sci-fi movies, where there's folks traveling backwards in time. Now, in our everyday experience, like you and me, we're just going forward in time, right? I mean, we're born, we live, and we die. That's how it seems to work. But we don't experience it backwards, and I'm not going back and say, it's not like I wake up tomorrow or I decide to go back like 20 years or my childhood, although, that'd be kind of cool. Now, the thing here is, weirdly enough, from the microscopic scale, the universe, the laws of physics, doesn't distinguish between the two. So here's what I mean. From a molecular scale, if you see atoms that shift around, if you play it forward in time and you play it backwards in time, you can't tell which direction it is. So it's the same thing. So let me give you some other examples. So this book, by the way, is pretty darn good. I'm just going to recommend it right now before I continue. It's called Time's Arrows. And it's by Richard Morris. All right, and it's Scientific Attitudes Towards Time, and it's an easy read. So Dr. Morris, he basically compares different theories of time, which dominated the ancient world, with a theory of linear time, which actually came from Judeo-Christian tradition. But I'm not going to go through this whole book. Point is, it's historical, it's scientific, and it doesn't have a million equations, which confuses people. So, you don't have to be a super nerd like me to read it. So, Time's Arrows, Richard Morris. So, he gives examples like this, for instance. So, let's just assume there is a extraterrestrial space vessel that's somehow floating around in our solar system. It passes close by Earth. Our scientists see it, and we're like, what is going on, right? So included on this spaceship are a number of these recorded discs, all right? So basically, they're like videotapes. Now, our scientists are trying to decipher, okay, which way are we playing the videotapes? So it seems like you can play in two directions, right? So you guys have seen videos. I mean, like, you can fast forward it or go back, right? Rewind. So now the scientists realize, hey, we need to figure out which direction is forward in time. Now, why is this an issue? Well, because, okay, the first videotape they examined shows a planet with 2 moons. Now, the scientists can see that the planet is rotating on its axis, but there's nothing in the sequence of images that show whether they're playing the disk forward in time or backwards in time, right? So, I mean, on Earth, you know, the sun rises in the east, sets in the west. But if we're looking at an alien planet, we don't know. I mean, from astronomical perspective, like, it'd be perfectly fine for it to go the other way around. You can't tell, right? So the next disc shows the planets revolving around the sun. Once again, we don't know which way to play it, right? Since both directions of time is perfectly compatible, both directions of revolution, I say, is perfectly compatible with Newton's law of gravitation, whether you're running time backwards or forwards. So you turn to the third disc now. So it shows, what does it show? It shows a cartoon that has a collision of an alpha particle. Alpha particle, by the way, is just a helium atom with no, no electrons. All right, so the collision of an alpha particle and a thorium-234 nucleus. All right, so it's a nuclear reaction happening. So the two combined, uranium-238 is formed, right? Now, is that really what's happening? I mean, if they played it the other way, it shows the uranium-238 breaking into thorium-234 nucleus and an alpha particle. Can that happen? Yes, it can. That's a nuclear decay, right? So that's perfectly valid. I mean, you could have it come together or you can have it separate. You don't know whether that's going forward or backwards in time, right? No way to tell. So every nuclear reaction that takes place can be reversed, essentially. All right, so the fourth disc. Now, by this point, the scientists are like maybe kind of frustrated. Hey, you know, these aliens provide us all these discs, but, you know, it doesn't tell us, you know, really like which way to play it, right? So we go to the fourth disc. All right, this one has another animated cartoon. It shows a bunch of molecules colliding with one another. Think of, like, say, air molecules, right? Like a cartoon version of that. You may have seen that in school. All right. And the walls of the enclosure surround them, right? So imagine putting a bunch of air molecules in a box, all right? So what is going on? Well, the disk shows basically these molecules bouncing around, and that doesn't tell you anything because you could go this way and hit something, or it could go the other way and hit something. You can play in reverse, and it will look indistinguishable from just, you know, like those molecules going this way and those molecules going that way. How can you tell whether you're going forward or backwards, right? Because, you know, that could entirely happen. All right, so now they're getting really frustrated. All right, going to the fifth disc now. This shows a number of strange-looking vehicles, which could be their version of cars moving on paved surface. So just imagine alien cars on their roads, right? Once again, they can't tell whether they're playing it correctly, whether it's forwards or backwards, because they don't know which end of the vehicle is a front, which end is a back, right? Remember, we're all looking at unfamiliar things, alien things. Now, if you look at a car here on Earth, yeah, like the one outside this window, I know it's going forwards, all right? But from playing this video of this alien car, we have no idea. All right. So, as Lord Kelvin pointed out, who, by the way, is a British physicist back in the early 20th century, he said, all right, so he pointed out something pretty important that we can figure out the direction of time. When energy is converted from one form to another, some of it must be dissipated as heat. So this relates to the laws of the second law of thermodynamics. All right. This is quite important because that is one fundamental way to know which direction the time is going. There's a realization from Lord Kelvin that, when something emits heat, if a hot object emits heat, it cools down, it only goes in that one direction, all right? So unlike molecular collisions, nuclear reactions, orbital motion, heat dissipation is a process that is not symmetrical in time. In other words, moving forward in time is different than moving backwards in time if you look at something like heat dissipation. All right, so the next video. All right, they realize this one's a little different because what does it show? It shows a hot glowing piece of metal, all right, held in a device that's like a pair of tongs, all right. All right, the disc, so when you play the disc, the piece of metal, it grows dimmer and dimmer, right? So the scientists realize, hey, it's losing heat to its cooler surroundings. So they know now we're playing this in a forward direction. Why? Because heat always goes from hot objects to cool ones. You never see it the other way around, right? Unless you apply energy. All right, so they don't see anything in the picture that might actually be heating the piece of metal up. So it can't possibly be the cool metal becoming hot. Like if they play it that way, it doesn't make any sense. All right. So think about we can also observe this. We observe this in life everywhere, really. Drop an ice cube into a cup of water, right? Eventually, the ice cube melts, right? You never see water just spontaneously form ice, right? Unless it's put into like a freezing environment, right? So when a piece of hot iron is plunged into water, the iron is cooled and some of the water evaporates, all right? So, you know, now I'm not saying that heat can't flow the opposite direction, but to do that, we have to expend energy, all right? So, I mean, obviously that's how a refrigerator works, right? A refrigerator motor pump heats from the cool interior into a room that's at a higher temperature. However, what I'm saying is that when there's no expenditure of energy, if there's no external source of energy, like a refrigerator, heat will always flow from a warm object to a cool one. The reverse process is never observed. So, now, this is the second law of thermodynamics can actually be explained in a multitude of ways. So one of the maybe more intuitive ways, which some people have said, is something known as entropy. Okay, so a common everyday perspective of entropy is disorder. All right, so basically, if you think of a so things basically entropy in the universe always increases. What does that mean? If we take it that case, it means disorder always increases. So now if you're gonna take it from the physics perspective, it's a number of microscopic configurations that are consistent with the macroscopic quantities that characterize the system. Okay, that sounds like a total mouthful. Okay, what does that even mean? All right, so let's consider this example of a bunch of gas molecules, air molecules in a box, right? And just going around, you never see very unlikely that all the air molecules just, like in this room, for instance, going to that corner over there and I suffocate to death, all right? You never see that. So why? Because there's a lot more possible possibilities of where these particles could be if it's spread out than if it's clumped in a corner. So systems tend towards higher entropy. So in this case, a really low entropy would be all the molecules going to a corner of the room, right? And that doesn't happen spontaneously. To do that, you have to apply some kind of energy, like we just said. So in other words, everything with time, all entropy increases. So if you started out with a clump of molecules in the corner, it's going to spread out across a room. That's just as there's more states, there's more possibilities that way for the molecules to go. All right. So and that we can tell that's a forward direction in time. All right, we got to take a short break. When we get back, we'll talk about some of the ways that time travel could happen, and as well as perception, actually, because that's something else that's really interesting with our brains. All right, we'll be back.
some of the other things you got going on.
Absolutely. So thank you for having me. I feel like I'm in the presence of like celebrities. Y'all real fans
It's just the shades, man. It's the shades.
So I think like 2000.
Growing up as a black kid in New Jersey, all I ever wanted to do was be a pro athlete. All of my role models were black athletes. And every time I would stare out the window and look at the sky and wonder what I'd be in the future, it always had to do with me catching some crazy football and scoring a touchdown. When it came to the point that I was told that I would not be able to play on an organized sports team for the rest of my life, it was something that I really didn't even know how to stomach in the moment. And I remember walking out of my cardiologist's office and just sitting in the hallway and breaking down for a few minutes just because it was something that I just couldn't plan for and couldn't account for. And I realized that in that moment, my entire life was going to be changed. And all of those dreams and hopes and aspirations that I had were going to go out of the window.
Okay, so we are back. You're listening to SG2 on Space. All right, and if I'm going to actually put a label to that, this is the first episode of this new year, 2020. Technically, this is episode number 57, and we're talking about time. So you can go on facebook.com/The Shen Show and follow me there, or watch this live, or at a later time of your choosing. Or you can go to YouTube. So go to youtube.com/u/CAST725. That's my YouTube channel, and it'll be right there. SG2 on Space. Support me, patreon.com/SG2 on Space. You can, get some recognition and keep the show going on there, right? Now, another thing I will just add is that we have shifted the time, since we're talking about time. We've shifted the time of this show, the live show, to be on Saturday at 1 p.m. Today's a little different. Had to get a few things set up. So with that, all that aside, let's go back to our conversation. So a little bit before we went on break, I was talking about how to tell whether we're going forward or backward in time, and I said nuclear reactions, orbits around planets, not orbits around planets, or just any kind of orbit, moon around Earth, all that, it will work the same way backwards. All right, like if we look at an alien star system, we have no idea, whether the image we're seeing is going forwards or backwards, right? Laws of physics work fine either way. Now, the laws of physics work differently, though, if we're talking about thermodynamics. So, there's something known as the second law of thermodynamics, which implies that the entropy of an isolated system never decreases over time. Actually, it doesn't say it increases over time, but typically it does. All right. So, example of that is the metal giving off heat. All right. A hot metal is always going to dissipate heat. Is never, you don't have a metal that's going to spontaneously heat up just because it's sitting there. You don't have a bunch of air molecules suddenly clump together in a corner and just stay there. Instead, if you have air molecules in a corner, tiny part of this room, say, it's going to float out and do that. You drop an egg on the ground, all right, it breaks. You never have the eggshells come back together and form a whole egg, all right? So from the macroscopic perspective, in other words, from the big picture view, right, of everyday objects, we see that as time going forwards, only one direction, right? However, as I also said, from the physics perspective, it's the concept of disorder is related to the number of microscopic configurations called microstates. All right. So things head towards a greater microstates. All right. That's one way to think of entropy. So that is part of a topic called statistical mechanics, which is another way of thinking about this, right? Which we're not going to go into because that could get complicated. So, but just realize there's a statistical character of this. And that's important because if you ask any particular molecule, say the air molecule, all right, and it goes this way or it goes that way, say it goes this way or it goes that way, it's fine if it's going forward in time or backwards in time. It's okay. But if you have a bunch of them, then you can tell, all right? So the behavior of a single molecule can be described by a basic time-symmetric law of physics, such as those of mechanics or even quantum mechanics, all right? So the individual molecule, in other words, has no way of distinguishing between the directions of time, all right? So now, but like I said, collectively it does, right? So, yeah. All right. Here's something that's of great interest to me and a lot of people. Now, I've thought about in the past. That's funny. I've thought about in the past of going back in the past. So, in fact, I'm thinking about it in the present as well. Okay. Point is, as I said, entropy increases, so it seems like, okay, I guess we're always going to progress towards the future, right? Is there a way to go into the past? Possibly. Okay, so there's something known as a, okay, so let's put why there's a problem with going to the past. Physicists really don't like the concept of going to the past because, like, you know, in the Back in the Future movie, Back to the Future, sorry, that's a classic one, because of the violation of what's known as causality. All right, so causality in time is a huge problem to physicists, and hence it's like, hey, if you have a cause, then you have an effect, right? So how can you possibly like, say I go backwards in time and I do something which basically ensures that I no longer was born, right? And what is that? I mean, like, that's just crazy, right? I mean, like, okay, so you went backwards in time to do that? How does that even work? All right, so, but is it possible with our current technology? Probably not, but there actually might be a way. All right, and one particular way is possibly a wormhole. All right, now this sounds sci-fi-ish, but I mean, for a while, black holes were considered sci-fi-ish until now we know they're everywhere. All right, so what is a wormhole? Well, a rotating black hole could create what's known as a wormhole, which is a theoretical link between 2 points of space-time, or even 2 points in different universes, which is, in my view, even crazier, or equivalent craziness. All right, so it connects basically between two distant points. I mean, if you guys have seen this is quite popular in sci-fi. You probably have seen the movie Interstellar, where, well, for you guys who watch sci-fi movies, where characters use, you know, these wormholes to really distant parts of the galaxy, and they're, you know, this time is all weird there. All right, so how would that work? I mean, well, now this is something that physicists are actually trying to figure out. Since according to theory right now, you can't really traverse through a wormhole. All right. The reason being, in fact, we don't even know if you can actually create one. All right. So we don't know what will happen inside of it because, like I said, it's generated from rotating black hole, and a black hole at its center, so to speak, is a singularity, and physics have broken down there. In other words, all the equations reveal, I think, infinities or zeros. It's just some crazy answer, so we don't know what's going on there. All right, so yeah, and there's also the fact that if you enter a black hole, it would seem like you would get crushed by the immense gravity, and nobody would survive anyway. All right, so No idea, in other words, how that will work. All right. In any case, now the other thing is that these wormholes could also go into a different space, right? So it's not like you go through there and you arrive exactly where you are, except a different time. You may end up on the other side of the universe, so that will be, different. That'd be weird. So now there is something known as a actually. Well, I'm not going to go into this because that gets way too complicated. But there's something called a Kerr, K-E-R-R black hole. So essentially, if you have that, they may not have a singularity in the middle, which in case, maybe you can somehow survive it. So, I don't know. Who knows, right? Okay. Now, we know going backwards in time seems pretty hard. What about going forwards in time? I mean, we're already doing that, but are there different ways of going forwards in time? Yes, there is actually, and this is where general relativity comes in, right? Or even special relativity. So, here's what I mean. Okay. Actually, Einstein basically found that, the faster you go, the slower your time gets, right? So what does that mean? So say I go into a spaceship. Actually, I don't even need to do that. Let's just talk about the astronauts right now. Astronauts up in the space station, all right? They are actually aging younger than us, all right? They're ridiculously, like, almost no difference. Maybe just shave off a few microseconds. But point is, they're technically, they are a little younger. So if you actually go, say, in a pretty fast spaceship, and you go off to the other side of the universe or the solar system, and then you come back, maybe 20 years will have passed by here, but from the experiences on the folks on the spaceship, then maybe 1 year passed by for them, right? Which is kind of crazy. So, in fact, you can do these calculations. So imagine a 15-year-old traveling at 99.5% the speed of light, okay? So he goes off and, I don't know, does something for 5 years, all right? So he does that for 5 years. When the 15-year-old gets back to Earth, he would be 20 years old. So what is that? That means 5 years have passed for him, right? However, his classmates, who was also 15 years old when he started, is now 65. So he basically aged 5 years, while his classmates aged, 50 years, right? This sounds all really theoretical. This is called time dilation, by the way, where time basically travels at different rates. This is all going to the future, okay? Just a note. This is not in the past. All right. This may sound really theoretical, and you're thinking, okay, well, you know what? Like, what does that have to do with me? I'm not traveling at 99.5% the speed of light, and sure, we're it's not affecting us. Actually, it is. So, you guys use Google Maps or GPS or whatever. It turns out that if you have a GPS, the receiver attempts to find signals from at least 3 satellites, and the GPS has to send out timed radio signals that the receiver listens to, all right? Triangulating or trilaterating its position based on the travel time of the signals. Challenge is the atomic clocks on the GPS are moving, and so they run faster than the atomic clocks on Earth. So it creates timing issues. They're not synchronous, right? So engineers have to make the clocks on GPS tick slower. So because traveling things the time, yeah. So in other words, they have to compensate for that, which is kind of crazy. So literally, the time dilation is actually being used all the time. Oh wow, time. All right. So GPS, when you think about it, actually uses general relativity here at work and time dilation, and yes, it is the satellite. If you look at it, technically it is aging, quote unquote, slower than people here on Earth. All right, so we have to account for that. Okay, all of that hopefully that gave you a big dose of, or at least a little taste, I should say, of all this time stuff. For the sake of time, we have to conclude here. Now, I will return, at least in the studio, I believe on the 25th at 1 p.m. However, I am also going to do this show regardless of the studio. So I will do a show probably at my location on the 18th. Also, I'm going to set it at 1 p.m. So in other words, all right, you guys, you just need to tune in on Saturday at 1 p.m. Houston time, and you can hear me live. As always, go to facebook.com, follow me, facebook.com/The Shen Show. Go on YouTube, youtube.com, look up SG2 in space. And please support me, patreon.com/SG2 in space. I could definitely use some patrons. This year, I'm hoping to make the show better, and hence having at least some financial support would be great. So that I don't have to do it myself, or at least all of it myself. All right. And you guys can get recognition, and if you donate more, we can even put an ad up on, in my show, right? So that'd be great. And for as little as just $5 a month. Okay. All right. With that spiel aside, all right, thank you. And, I typically do end with a closing phrase. I did not talk about aliens this time. If I did, this would have been made more sense, I suppose. But I will still say this. Look up, because you never know what you will see. All right? Unless you're driving, then please don't look up. But otherwise, look up, because you never know what you will see. Okay. See you guys next week, 1 o'clock Houston time. All right. This is Shen out.
Peace, it's Brother Atum Ra, and you tuned in to Action One Network.